morning, everybody. I want to thank the organizers of this conference for the invitation to share our experiences here with you about LC3 and the implementation. As you already heard, I am part of the core team developing the LC3. We began the collaboration with Lausanne in 2005. Me, myself, I have been working with calcined clays since 1996, more or less, and I have been taking care of the part of going into industrial applications. So I've been working with several companies implementing projects. I accompanied Oyak and Simpor in Ivory Coast in the first application, the pioneer application in the world. Also, I was the one evaluating the raw materials for Argos in the Rio Claro plant. So I have a wealth of experience in practical applications, and today I want to discuss briefly these ideas with you. As I said before, we are a global team with headquarters in Lausanne, EPFL. It was originally a project funded by the Swiss government. The idea was to look for a very quick dissemination of a technology that could drastically reduce carbon emissions in the cement industry, which we all know it's about 8% of global CO2 emissions. And through the collaboration with our university in Cuba, but also the Indian Institute of Technology, represented here by Professor Shashank Bishnoi, we were all able to, spread out to different continents, different countries. And very recently, what we created, the TRC Technology Resource Center in Kenya, in Meru. The idea of these centers are to assist the industry into the implementation of the technology by providing all the testing and experience and advisory service. In terms of the timeline, it is very impressive how the life of our team has changed in the last 15 years. As I said, I began working with calcined clays in 1996. In 2004, I came to Lausanne and I presented Professor Scrivener the ideas how we should work in clays, and she jumped to the ceiling. She said, yeah, we're going to do that. 1 year after, we had the funding for the first part of the project. The original idea was to, instead of making a high purity metakaolin, to do a low-grade clay, a clay with a lower kaolinite content, which is widely abundant in the world, to use it as a normal porcelain. But then, while we were doing the research of this material, we realized that through the combination of calcined clays with limestone, there was a synergy. And the synergy was the reason to form new hydration products, alumina-based hydration products, and that was the base also for increasing the clinker substitution rate. And this is how we came across the concept of the LC3. This happened in 2009, more or less. So after 5 years of direct work, there were two main papers published. One was the paper on low-grade clays in 2011, and soon later, in 2012, the paper on the synergy between alumina and carbonates. That was the backbone of the LC3 concept. And very, very quickly, we were able to scale it up at the industrial level. We ran the first industrial trial, calcining 400 tons of clay, kaolinitic clay in Cuba, in a very old, outdated plant. We were able to produce around 300 tons of cement, and we were able to massively use the cement. I'm talking about more than 11 years now. And by doing this, we were able, because we were not allowed, it was a new cement, was not in the standards, we were not allowed to use it in commercial buildings, so we decided to put it in blocks. And these blocks were exposed on the seaside, and that has given us the possibility of studying durability, especially in marine conditions, for these elements for many years. In 2018, we were able to set up the first pilot plant. It's a small plant where we run industrial trials. I'm talking about 100 kilograms an hour, but this is very useful because normally people think that you can go from the lab investigation directly to a plant. So you go from investigating a few kilograms of material, and then you go to produce 30 tons an hour. So you need an intermediate level to test all the industrial parameters, and this is why we were able to do that. In parallel, we started working with companies like Argos, and Argos decided to launch the first industrial production. I can tell you now that in these years of production, they have produced more than 8 million tons of cement containing calcined clays, and they have made a lot of buildings, bridges, tunnels, and a lot of applications. And then very, very quickly, Simpor, Oya came with a plan in Ivory Coast that was also a breakthrough, producing the DOH clay, and also it set a milestone in the production, and now this company is expanding to several other countries in Africa. Today, as Professor Karen Scrivener said, we have this is the world map of plants. We have more than 19 plants in operation today, including the ones in Brazil. Only Brazil is producing 3 million tons a year of calcined clays. And, but also, those are the ones on the public domain. We know that there are many other projects that have not been communicated so far, but they're in a very good place now to start the production. And by doing this, only this year, we're forecasting that the production of calcined clay will be around 15 million tons. 15 million tons means that we're going to save around 9 million tons of CO2. But we're not happy with this, because our target is to produce up to 400 million tons of calcined clay, and by doing this, we're targeting, more than 500 million tons of CO2 to be saved, and we hope that we can do this in the next 20 to 30 years, meaning this is going to be a significant impact on the climate change. All of this massive advancement, because you realize in less than 15 years, we have been able to develop a new product, to develop the technology, to implement it in real life projects. It has not been a result of a small group of people. It's a big community. It's a unique collaboration between academia and industry, industrial partners, academic partners. And this is an example of the Ryland Technical Committee 282, which was a joint work of the industry and the academia. More than 70 people, scientists, industrials, worked together for 5 years, and they prepared, they went through all the fields related to calcined clay production, use, investigation, and there's a topical collection of 10 papers published in Materials and Structure doing this. Also, when you realize the amount of groups working in that area, you realize that there's a lot of art scientists working in that, in also distributed throughout the world. So right now, I tell you, almost everywhere, there's no country where people are not investigating on calcined clays. Everybody is looking for calcined clays, and everybody reckons that this is going to be the future of the industry. So to summarize this, we right now, after 10 plus years, we have a knowledge and experience of how to choose the clays. We know how to choose the clays now. We can tell them, these clays are suitable, these clays are not good. We have different choices. Machinery producers, today we have more than 9 companies offering equipment for clay calcination. Some of them are here in the fair, and they have stands, but it's no longer a problem to have access to suitable machinery for clay calcination and also for grinding the clays. The admixture industry, which is also represented here, has made a lot of work. 8 years ago, using plasticizers in concrete with calcined clays was a challenge because of the high water demand. Today, there are products that resolve this problem, and this is no problem at all. Also, standards. Many countries have developed standards adapting. The first and most important ones was the EN 197, Part 5, that was able to reduce the clinker content to 50%. This is a breakthrough, because before it was 65. But also when you look at the US, the ASTM C595 already has that. In India, Professor Bishnoi was able to get the Indian Standards Committee to approve a standard representing the LC3 with lower content. And even today in Africa, there are countries where 35% clinker in these systems is approved. We have, as Professor Scrivener presented, we have a critical mass of successful applications. So today, nobody can question that this is a lab development, a scientific development. It's also an industrial process. We have evidence of very good durability, especially in marine conditions. And we have proven that we are able to reduce the carbon emissions. Very few technologies scale up so quickly. I'm talking about technologies like geopolymers, for instance. They have been there. I remember me translating a presentation of Professor Krivenko back in 1986. So this technology has been there for over 50 years, and today we only have a handful of factories producing the material. In this case, we have gone very quickly in the production of that. However, we still have some stumbling blocks, and it's normal. So as we're going in the implementation of the technology, we always have problems that arise. One of them is the purity of type of clay. The other is the technology for calcination. Those are the questions that we receive every day. How can I get my clay? Is my clay suitable? What is the technology I need to do that? I have an issue with color. My clay is red. How can I change the color? And also grinding. Lots of people say, is the same to grind calcined clays that to grind clinker or normal cement? And there are other things that are going to be addressed by Professor Bishnoi in his presentations, like rheology of cement with calcined clays and durability in concrete. So he will make a presentation, so I will not address that. In terms of clay type and purity, we are seeing in our experience that clay is a very heterogeneous material. This is this diagram here on the top. It's the results of testing more than 200 individual samples in one quarry. And you realize that kaolinite content varies from 15% to 55% in the same quarry. So you walk 50 meters and you take a sample there is different from the sample you get here. So it's a very complex material, and you need to make a very good mining strategy to operate the plant in order to optimize the reserves that you do that. One of the things that we are doing more and more and more, this is also an industrial trial we ran a few years back, is to blend, to understand the clay deposit and to blend different clay types in the clay in order to target the optimal kaolinite content, minimize, for instance, limestone and others. This is an example of a work we were doing in Africa. This case is in Angola for the company Simangola. They had the clay in their own factory that had a kaolinite content about 30%, and we were able to find a neighboring quarry where you are able to blend this clay and you expand the reserves of material, and also you improve the quality of this material. As Professor Scrivener said, we are now targeting 40%, but in recent projects we have realized that you can even have a lower kaolinite content. I'm talking about 35% kaolinite content, and still you get very, very good results. This is also the result of optimization of that. In terms of calcination technology, everybody's asking, is there a difference between the different calcination technologies? Is it better to use a flash? Is it better to use a rotary? There are issues of economics. I will not go into these issues. I will go only into the reactivity of the material, because when you see right now in the world, it's a trade-off. I mean, more or less half of the plants are made on rotary, the others are made on flash. I mean, there are different options for people. There are other technologies, but they are not so matured right now, so so companies are not using them. I have an issue here. Yeah. This is for you to have an idea of the installed capacity. Also, there's no agreement, there's no real trend in terms of what is the daily capacity. You have plants that are producing as low as 100 tons per day, and there are others that are producing 1,200 tons per day. So there is a great variation also in there. It depends on the local conditions of the plant, but this is also very important to consider. Then you have the option of flash calciner. Today there are several companies producing very good flash calciners in the world. And you also have the issue, the possibility of a rotary kiln. Every technology has advantages and disadvantages, and they have been discussed elsewhere, and everybody knows the advantages and disadvantages of the technology. What we did was What we did was an analysis. We took the same clay. We have pilot facilities for rotary, but also for flash. And we were able to get the same clay, prepare the same clay in the same way, and calcine the clay in the two technologies and compare the results to see if there was an improvement in reactivity or everything. The first thing we realized that we were, where you see there, static calcination, this is rotary, and then you see FC, this is flash calcination. We were calcining, the optimal temperature was 900, and in rotary we were using 750, and we had the same amount of amorphous, which is more or less an indirect indicative of reactivity of the material. In terms of strength, we were able to see that there's no major difference in any age of the strength of the material, so it's very much the same, and I encourage you to check the paper that we have published on that. So basically you can say that you get the same product using any of the two technologies. Then you have to go into the issues of economics, cost, and everything, but this is not the aim of this. In terms of color, it was already discussed by Karen Scrivener that many companies don't like to have a reddish or a pinkish cement. But I can tell you, if you have a clay with a low kaolinite content and you want to boost the reactivity of this clay, like you see here, one of the things you shouldn't do is to do color control, because the presence of iron creates some amorphicity in the system that enhances the reactivity of this material, and this is already proven. You see, we're talking about a clay here that has 47% kaolinite content, and another clay that has 72%, and this one, if you don't do color control, you can improve the reactivity. But okay, I understand the point that many people don't want to have a red cement. So what you can do is you can control the cooling conditions in the system. This is also a paper I published on that. And in practical terms, what you have to do is in the cooling chamber to introduce or to find a way to do the cooling of the system in a reducing atmosphere, so that you can have different phases of iron, either hematite, which is red, or magnetite, which is black. We have clear evidence of that doing the test. This is a result of testing different clays with different iron contents, different things. What we're seeing is that when you have a very high iron content, I'm talking about higher iron, higher than 10%, you begin to see a drop in the specific surface that can basically compromise the reactivity of the material. But when you go and measure in cementitious system, the impact is not, even for the higher iron content, the impact is not very relevant in terms of the reactivity. In terms of grinding, this is also challenging because we're having a ternary binder. You have many products at the same time, different hardness of these products, so you can have over-grinding or under-grinding of some materials. When we run the first industrial trial, we were having, this is the residue on the 90 micron sieve, and we were having the clinker very coarse, and we were having the calcined clay very fine, which is the worst case scenario, because you have a low reactivity in your system and you have a very high water demand in your system. So, but this is how we ran the first trial back in 2013. We didn't have the knowledge we have today. And, but then we realized that it is as easy as using commercial normal grinding aids, especially of the types TIPA, TEPA. So TEA, TIPA, they work because the problem is that you create coatings on the steel balls. And these coatings prevent, and also on the walls of the mill, prevent the clinker grains to be further ground. And only by doing this, when you check here, we were able to sort out the different fractions and to measure the amount of clinker in the different fractions, and we were able to see that if you increase the dosage of grinding aids, you increase the amount of fine clinker, very fine clinker on the 7 microns at the cost of reducing the very coarse clinker. And this is having an impact there. Unfortunately, it's not, there, an impact. You see, you're able to raise the strength from 8 megapascal at one day to 12 megapascal at one day. So there's a lot of tricks you can play with your cement, especially if you want to have a high early age strength. I mean, 1 day, 2 days, 3 days. You can play also with the sulfates, with the alkalis. There's many tricks that you can do that. And the other thing that we're doing more and more, especially for the ready-mix industry, is instead of producing a cement, we're doing a separate grinding, and we're producing mineral additions. Either what we call LC2, which is blending 60% of calcine clay, 30%, 35% limestone, and 5% gypsum. Gypsum, people always ask, why gypsum? Because you need to sulfate the system. Because of the high specific surface, there's a boost on the hydration of the product, so you need to put more gypsum in the system. You put it automatically there. And also in cases where you're using Portland limestone cement, instead of making LC3, we take out the limestone and we use the so-called C2. In both cases, we're having outstanding results. And this is a good option for the ready-mix industry to extend their Portland cement, the use of Portland cement. With this, I come to the concluding part of my presentation. I mean, as conclusions, you have seen that in a relatively short period of time, all the industry has adopted the technology, all the scientific work has been carried out, a lot of scientific publications, a lot of things, but they haven't stopped there. There's a lot of introduction in the industry, and it has evolved from a research work to a sound product, which is now produced all over the places. A large community of scientists and industrials are busy working to improve and to respond to all of these questions that I put here. And the group, the number of people is growing and growing and growing. Lots of hundreds of PhD students, universities everywhere. For those willing to introduce LC3, there are technological choices in terms of calcination grinding. I mean, it's already out there in the market, and the product has proven to be competitive in all industrial levels, standards, applications. I mean, there's no doubt today that you can make a good concrete using calcine clays. With this, I also mentioned that we are holding, our project is holding activities, we call them LC3 days, where we present the latest developments. This time we're running the next LC3 day in Oman, and the interesting part of that is that we're starting a new plant in Oman, in north of Muscat. It's called the plug and clay. It's a very innovative approach for machinery, and the site will be, the event will include also a visit to the plant, which is already in operation. And as Karen said, it's going to be an interesting opportunity for those of you who can join us in Cape Town in February next year for the next conference of calcine clays. Having said that, again, I thank you very much for your attention, and I'm looking forward to if you have any questions. Thank you.
Thank you so much for a wonderful talk. For me, it's really a great morning of learning about LC3, and I guess also for people from the audience. Are there any questions? Yeah, I see there one question.
Hi, I'm Rufat Oğuztur from Norm Cement. We are looking for the technologies for the calcined clay, but I'm interested in is there any chemicals to reduce the water demand of the LC3 type cement? As we know, it's high water demand cement compared to normal Portland cement.
Can you please speak louder?
Yeah,
Cool.
can you hear me? Okay.
Now, yes.
Now it's better, yeah.
Yeah. Is there any test or something you did that to reduce the water demand of the LC3 type cement? As we know, the LC3 type cement's water demand is a bit higher than the ordinary Portland cement. So you showed some chemicals, test with chemicals, amine or etc. Is there any test to reduce the water demand?
So the question is, is it possible to reduce the water content?
Yeah, water demand, water content.
Water demand.
Water demand, yes. Well, as I said, the industry has done a great work. There are networks like Innovandi, where they have projects trying to understand at the fundamental level why are calcined clays increasing the water demand. Right now we have the knowledge, we know what is happening there, and the moment you have the knowledge, you are able to tackle that. And I can say most of the companies right now in the market, talking about Sika, Criso, Mapei, and many others, they have already developed tailor-made products for calcined clays. Many of them are now in commercial distribution. I mean, you can buy them in the market. And when you use this material and these admixtures, I am using them from all of the companies. You don't see any problem in rheology. I mean, you can counteract you can have the same water to cement ratio. You only have to use a little bit more of plasticizer. And also, one of the main problems we had with the calcined clays was the slump retention. The time was very short. It was less than 1 hour. So right now, I can tell you that we are producing concrete where you can have up to 3 hours of slump retention, which is for ready-mix industry, it's ideal. And I can tell you that this is not going into a much higher cost. I mean, the concrete, the cubic meter of concrete costs more or less the same, and this is thanks to the efforts of the industry trying to resolve this problem. So today I can say water demand is no longer a problem, but Professor Bishnoi will discuss that in detail. He will show you some examples.
Okay, thank you so much. It's very detailed information.
There's another question on that side.
Hello. So this is Ihsan Özkan from Nokia company. Thank you very much coming over here, Professor Shashank. Enjoying the weather, the atmosphere. I hope you enjoy it. So as my country is having a lot of earthquakes, the cement industry, of course, is very important to keep the life safe. So your presentation is very interesting. This LC3 cement seems to be alternative to typical cement product. But what about the cost-wise? Is it really expensive? Thinking my country is investing heavily to cement. So if it is a kind of Mercedes to Lada brands, that's not applicable. So if you can share your opinion.
Thank you.
Thank you.
Thank you very much for your comments. In terms of cost, it depends always on the cost, on the royalty you have to pay for the original clay. If you are the owner of the mine, let's say, normally, in my experience, what I have seen is the royalty cost is around $5 per ton of clay. So if you manage to keep the royalty cost below $5 per ton, because there are places where you have to pay $20 for a ton of clay in North America and some other places when you buy from third parties. But if you manage to keep the cost below $5 per ton, the total cost of calcined clay will be below $15 per ton. So it's a very good cost when you compare it to the cost of clinker, which is between 35 to 45 US dollars per ton. It's very. But again, this is not a rule. It depends on the royalty cost. It depends on the technology you're using. It depends on the local context, the cost of transportation, and everything. But more or less, as I can say, the cost of calcined clay ranges between 15 to 25 US dollars per ton. Worst case scenario, 25. Best case scenario, 15 US dollars per ton, more or less.
Thank you very much.
Thank you. Oh, I see more questions popping up. There's a question over there. While the mic is walking there, I'll make a climate comment. I think that for you, Cuba has a very good climate, right? Coming from Netherlands, the climate benefit of being here a couple of days was bigger.
Yeah, but we have hurricanes too.
All right, yeah.
And hurricanes, because of climate change, they are getting worse and worse.
Right. Okay, next question, please. Who has the microphone now? There, yeah.
This is Hakan Arden Kahraman. I'm quite interested about the color concept you mentioned, that the market has got this perception, accepting the pink or reddish color. Sometimes playing on the weakness, make it to your advantage. Working with maybe architectural firms, etc., accepting the pink or the reddish color as architectural feature, then it becomes a strength rather than weakness in the market. I want to hear your comments on that one.
Thank you very much for these questions. All the questions here have been spot on. Very good questions. There's always the issue of color. Normally, the clients think that if they get a cement with the different colors, the company is cheating them. I mean, they're selling you something that is not good. However, we're seeing, for instance, Cement in Switzerland. They are producing LC3. And they decided not to do color control. They are selling a red cement, and people are more than happy with it. Like Karen said, they find it very lovely. We have seen also in India, Shashank and Professor Bishnoi can talk about that. In India, they were producing some tiles out of red cement, and people were willing to pay twice the price of the tiles for the red tiles. So, because normally we're seeing, I have slides in other presentations where you see iconic buildings in Europe. They put pigments in the concrete to make it look red. And the pigments, they are very expensive, first of all, but second, they compromise the properties of concrete. Yes, you can do the color control, but remember that by doing color control, at least you will not improve the properties of your clay, the reactivity of your clay. In the worst case scenario, you will have a small compromise. You will reduce a little bit the reactivity of the calcined clay. As I said before, it does not reflect more or less in the final strength of the cement, so it's irrelevant to put it in a way. But if you don't control the clay, you boost the reactivity of the calcined clay, and that also has an impact on and that was the case of Cement in Switzerland. They had a very low kaolinite content, but by not controlling the color, they were able to boost the reactivity and then yet make a 42.5 cement. So this is an open discussion. I remember Argos in Colombia, there was a big, because it also depends on how you sell the cement. For instance, in South America, 70% of the cement is sold in bags. And the bags are sold in the stores, and people go to the stores. And when people see this red cement, they say, oh, I don't like that. But if you sell the cement in bulk to the ready-mix companies, and when you see a big company using a red cement to produce, it brings confidence to the people. So it's very, and you can also have a campaign to advertise for the color and everything. So there are many things that can be done in that sense.
Thank you. Next questioner, please. Yeah. Oh, sorry, the microphone is further back. You will be next up.
Thank you very much for your presentation. I was just wondering, you told in your presentation that you have been processing calcined clay as rotary and flash in two. And I was wondering if the energy is the same in the two products, like energy consumption wise.
I recommend you to check the paper listed there. It was published in International Cement Review, where I did a review of the energy consumption and the ranges in different plants, and yeah, it's more or less the same.
More or less the same, because
More or less the same.
I think
It
that
ranges in depending on the type of technology, and even on the producer of the technology. But it has a range, and the range is more or less the same.
okay, because I think in the flash the tonnage is a little bit less than the rotary because of
Yeah.
the
Yeah.
okay, but
Yeah.
the specific energy consumption is more or less the same.
The problem with the flash is that normally you have less than 400 kilocalories per kilogram, but then you have to dry the material before you feed the material to the system. And in drying the material, you spend 120, 130 kilocalories per kilogram of material, and then it goes up to 500 or something. So, whereas in the rotary, also depends on the type of rotary. The newest design is a double body, where you have a dryer and a calciner, and the dryer, and there you can get 520 kilocalories per kilogram. I mean, it depends on each case. But yes, it's also an interesting point.
Okay,
But my point here was to say, because sometimes you see in the literature, the clay in a flash calcination is more reactive than the clay in a rotary. As far as I am concerned, this is not true.
Okay, understand.
And I have scientific proofs of that. And also there are other groups working on that, and they have similar conclusions.
Okay, thank you very much.
Okay, thank you. The next questioner is over there. The microphone is coming to you.
Hello, thank you very much for this fruitful session. And I have a question about alternative raw material that replaced the metakaolin. Before producing the metakaolin, you are using mainly kaolinites. So, yeah, you mentioned about different alternative like drying savage sludge or the dry sediments and other stuff replacing the kaolinites. So, do you have any real example in the world that making this kind of production and they have some good durability in terms of the aspect, rheology and physical things? The
Yeah.
first question is that. I
This
have
is
the second
also-
question.
Thank you very much also for the question. This is very interesting because in many countries, for instance in China, you are not allowed to open a new pit. Meaning even if you have the clay quarry, you can start extracting the clay. So you have to go to waste materials, waste from other products. We are seeing very interesting results in the dredging sediments. So you have to dredge, and the sediments, one of the projects is in Belgium and also in the Netherlands, where they have to, they have to allocate, they have to put these sediments somewhere, and they don't have space. Those are very small countries, and they have to pay a lot for the space. And in this case, they are recycling the material. The problem in these dredging sediments is that the kaolinite content is a little bit low. We're seeing this is between 30 to 35% kaolinitic clays, but also you have 2-to-1 clays in there. You have illite, marmoronite, and what we're seeing is that if the total amount of clay minerals is up to 50%, you are in a very good shape, even if you have 25% kaolinite content. I mean, you have to work with the calcination temperature, probably elevate it a little bit more to dehydrate the 2-to-1 clays, but yeah, this is a good case. Another interesting case, very interesting case, and I've seen this in Portugal, in the US, and also in many places in South America, where you have a plant producing sand. You extract the sand from the quarry, you have a trommel where you wash the sand, and you get at the end a slurry, and this slurry goes to these press filters, and the material coming out of these press filters is very pure material. I tell you, in Portugal, kaolinite content is around 60 to 70% kaolinite content, and this is a waste material. It's only a company. There's a company in Portugal that is producing 10,000 tons of sand per day, and they are producing 1,000 tons of this waste per day. And they're dumping it in a place, and it's full of, it's like a place, and they don't have a market for this material. And this is a very interesting opportunity. This is happening all over the places in the US and also in South America. So this is also an interesting opportunity. Thanks.
Thank you for the answer. And the second question is about the alternative fuel. You mentioned about the Jura cement. If I'm not mistaken, they are using 90% of alternative fuel during their traditional production of cement. Are they using alternative fuel in case of the clay calcination, calcined clay production, I mean?
No, because they had access to an existing quarry that had all the permits and everything, so they were able to exploit. Their problem is that this quarry, typical of the geology in Switzerland, is low in kaolinite, so they have kaolinite content around 30%, but they have also 2-to-1 clays.
I'm asking the alternative fuel. Fuel, not raw material. I mean the coke, petcoke, something.
The fuel,
alternative fuel.
Alternative fuel. There's a lot done in that area. For instance, I can tell you there's a new plant now commissioned in Spain that is going to have a biomass gasifier next to the plant, so coupled to the kiln. And by using this, it's going to use between 80 to 90% biomass. So only 10% solid fuel, coal. And we're estimating that we're going to drop the carbon emissions from 220 down to 40 to 50 kilograms per ton. That is going to have a huge impact in the total CO2 content of the cement using there.
Okay. Thank you very much.
Okay, thank you. I think there is a gentleman over there with a question. So could you pass maybe the microphone? On the third row, and then I will finalize with you. I think you had a question? Sorry? No? Okay, then please go ahead.
Thank you, Fernando, and your team's good presentations. And also thank you, Karan and teams, for the research of the calcined clay. You can give the add value for the LC3. And I wanted to say that all cement producers, we can use these two professors' experience in the productions of the LC3. Only I wanted to say, add your ideas, one thing, is the alternative fuels in Ivory Coast simple calcined clay production lines, 100 we can use the calcine in the calcined clay. We reached the 100% is the biomass we can use. Also, I give the small correction for your presentation. In the Ivory Coast, starting the production lines 2021, 30 August. Is the 30 August is very important for the Turkish life. Therefore, this is the important things. Another one is the 23 is 29 October is the Cameroon. I believe we can starting the Ghana end of this year, and the Suzelas plant that is Simpor in the Portugal end of the first quarter of the next year. Have the more opportunity all the world for produce the LC3, and I want to say that the all research for you. Thanks a lot again. Thank you.
Thank you very much. Thank you.
And with that, I would like to...
If I may reply very quickly?
Sure.
Yeah.
Certainly.
Thank you very much, Mr. Swat. It's really an honor to talk to you and to listen to your comments. I will change the presentation because I used the information that was on the public domain. It was mentioned in 2023. I know you started before because I was part of that. But yes, I will, now that you're saying this, and I have to say also that Simpor is a world leader in calcined clay productions. This is why it is even more interesting for me to be here and to share my experiences with you. Thank you very much.
Thank you. Thank you so much for this wonderful lecture. In view of the time, I think we move on to the third speaker, but I'm certain that during coffee break or lunch, maybe you will be available. Thank you so much.
You're welcome.